morning. Once again, I will welcome you to this lecture on foundation engineering, and we have discussed about the earth pressure theories and stability analysis of earth retaining wall. And I have quite elaborately I have discussed the earth pressure calculation for different conditions, like when the soil retain the cohesionless backfill, and then there are different theories at the Rankine's theory, Coulomb's theory, and Rankine's theory there is some limitation, that means it should be a vertical wall, smooth vertical wall and level backfill. However, Rankine's theory as initially is mentioned that, but if it is level backfill, inclined backfill, or the instead of vertical, if it is not vertical also, how to take care, that also I have discussed. And finally, using those earth pressure theory, actually our primary objective is actually to analyze the stability of earth retaining wall. And for earth retaining wall, that when we want to do stability analysis, we need to know what are the different forces acting on the wall, and lateral earth pressure is one of the most significant loading on the retaining wall. So, because of that we have devoted a significant amount of time for finding out the earth pressure for different condition. And again, initially we have started with cohesionless backfill and we have discussed with different theories, and then later on we have also discussed with C-phi soil backfill, C-phi soil backfill, and how they change and how their pressure diagram, how their what is the total thrust comes to the wall because of the backfill, what is the point of application of the thrust, all those things we have discussed. And also I have discussed the stability analysis of the wall based on that. And at the beginning, as introduction, also I have mentioned different types of retaining wall, and some of the things like internally stabilized, externally stabilized, like that we have divided. And we have mostly what we have considered, they are all externally stabilized. Okay, so that gravity retaining wall or cantilever retaining wall or gabion wall, all those things actually externally stabilized wall. And there are actually another type of wall, that is called internally stabilized. Why internally stabilized? Because we use some reinforcement, and that reinforcement itself and put it in the soil, and that itself helps to stabilizing the wall. So, because of that, so I may not be able to take that internally stabilized earth wall in detail, but I will just give you the introduction how we design internally stabilized earth wall or earth retaining wall, reinforced earth retaining wall, and then finally I will try to summarize whatever we have discussed through 2-3 weeks, that is stability earth pressure and stability analysis of retaining wall. So, let me take to the first slide, which is actually reinforced earth retaining wall. And you can see this figure also I have shown at the beginning, and that you can see that this is actually the wall, this is actually wall actually, but this wall, unlike gravity retaining wall or cantilever retaining wall, they are very light and they are not really wall, they are actually facing element. And this facing element actually, if I put any load, it will not be able to hold actually. So, because of that, what is the mechanism here actually? This facing element connected to some reinforcement, you can see at different locations, and those reinforcement actually placed within the soil itself. And when there will be backfill, soil is fully backfilled here, then what will happen? Because of the soil pressure, this facing element will try to move this direction. Okay, when it will try to move this, and since the reinforcement is connected to this, then the reinforcement will also try to get pulled outward, and then because of this and that time, that between the soil and this reinforcement, and generally we take this type of construction, we use granular soil. So, granular soil will have some friction and the reinforcement will have some friction. So, between this soil and material and the reinforcing material, there will be some frictional force will develop, and that frictional force, if it is enough, then this wall will be will not move, it will not fall, it will stand. So, that means to prevent falling of this facing element, what you have to do? You have to put this reinforcement sufficiently inside the soil mass. Okay. So, to put this sufficiently inside the soil mass, then how much is the sufficient? That has to be calculated actually based on some theory. So, that is the thing I will try to discuss very briefly. So, what will be the length of the reinforcement inside the soil? So, and you can see that it is shown here actually there is a this is actually H, the spacing, two types of spacing. This is one spacing between this and this, and there is another spacing is this actually, at one is S, another is H. S is this and H is this, suppose vertical spacing. So, this is one level of reinforcement, this is second level of reinforcement. Between this whatever distance, that is suppose H, and again if the wall is quite long, then laterally also in some interval you have to put reinforcement. So, that is if this is the one, then next is this one, then this is the one. So, this is the spacing between these two, suppose S, then and so what will be the total tension will load or tensile load will come to the on the reinforcement. There is a mechanism to calculate. So, what we can consider? We can consider that if I consider this reinforcement, then half distance here and half distance above will be zone for it. So, because of that, and similarly if I consider this one, half from this side, half from this side, that means for a particular reinforcement from both side half half and from the top and bottom also half half. So, that is why gamma times z, suppose if I consider at this point, what is the lateral pressure? Gamma z times K A, and if I consider within the depth of H is constant average, because I will just show this one. This is the reinforcement level, and if I earth pressure diagram, if I do like this, and I am considering this portion for this rod. Okay. Here actually lateral pressure something, here also lateral pressure is something. So, this point actually average of these two. So, because of that I will consider at this point what is the lateral pressure, that is enough. That is why if this is Z, if this is Z, so gamma times Z is the vertical pressure. If I multiply by coefficient of earth pressure, it will become lateral pressure, and then I will take S spacing and horizontal spacing and H horizontal spacing. So, that if you multiply, then I will get the force, and that is the amount of force comes to the rod, and that means this much force because of the backfill it is giving to this rod, and which will pull you this side. Now, I have to put the rod now, the reinforcement now inside the soil, which is this is the failure plane. Suppose if this is the failure plane will be something like this. So, failure plane will be something like this. So, you have to put the soil or the reinforcement within the soil mass sufficient length, so that the developed force will be equal to this, at least equal, it should be more than that. So, how to find out that force? That force again can be calculated if that at that level actually vertical pressure is gamma times z. If I multiply by tan delta, that gives you friction, and I will get the friction from both sides. So, actually, so over the entire length, so L will be there, and your width length into length multiplied by. So, this is actually gamma z, tan delta is the pressure. So, this is the reinforcement area. Suppose gamma z tan delta is acting here. So, what will be the total if I multiply by L into W, sorry, L multiplied by W. So, L is this one and W is this one. So, that means surface area I am multiplying. So, gamma z tan delta is the friction and L multiplied by W is the surface area, that become the frictional force, and since the each reinforcement will have friction both at top and bottom. So, because of that we are multiplying by 2. So, that means total frictional force developed actually this, and total tensile force because of the backfill coming onto this is this. So, this has to be balanced by this, and if I adopt a factor of safety suppose 1 or 1.5 or 2, accordingly I will get a, if other things are known, I get the length, how much length is required. If I fix a a reinforcement of 2 centimeter width or 3 centimeter width. So, W is known. So, and tan delta, gamma, z, everything is known, only unknown will be L. So, we can find out the L. So, that is what I will go to the next slide. You can see here. So, if I know the factor of safety, if I apply some factor of safety, suppose this factor of safety is known, suppose 1.5, and this I consider a reinforcement at some depth. So, z is known, gamma is known, tan delta is known, width of the reinforcement is known, and only unknown here L, and here gamma, z, k, s, h, everything I have, these are all design parameters. I will initially assume, then only thing is from this calculation I will get a L. So, that L actually how much actually based on calculation we get L minimum. That means how much, this is the, if I assume that this is the failure wedge, this is the failure wedge. So, that means within this zone reinforcement will be inactive, because soil is moving. So, there will no friction develop there. Only thing, if I go beyond this, that zone only will give you frictional resistance. So, because of that I have to calculate what is the minimum distance is required based on this calculation you are getting. So, your L Rankines means what? If I have a failure plane like this, then from the geometry this is h and I know this angle. So, I can find out this length. So, this is actually Rankines length, and this is based on frictional resistance L minimum. So, these two together will be actual L total L total, and so based on that I can calculate, and L total of course based on calculation you may get some value, but there is a guideline that you should not give less than 0.8 times h. Okay. So, 0.8, so if h is suppose 6 meter and 0.8 actually that means 4.8 meter, you have this is 4.8. Suppose based on this calculation Rankines length, and based on this calculation if you get suppose 4.5, you should not give this, you should give 4.8 meter. So, this is a basic principle of reinforced earth calculation. That means everything same, I will consider the Rankines failure plane, and then based on that I will assume a vertical spacing and horizontal spacing, and based on that you can see at what interval I will put reinforcement and horizontally what interval I will assume, and based on that what should the length required I can calculate from here. Okay. So, this is some basic about reinforced earth analysis. Okay. So, I will not go beyond that, and this wall again, this is actually calculation. Again what additional we have to do, I have given the length, but whatever force I have calculated, so whatever T you have got, because of this tension it should not tear also. So, based on that I have to find out or design the thickness also. So, I should know the material strength, and based on that T divided by area, or I can find out T divided by sigma, from there I will get the area, and that means from there actually if I consider width, then I will get the thickness also. So, that is one thing to be designed, that it should not fail, and again there are many other analysis is there, stability analysis, which I will not discuss. So, that I will put it beyond the scope of this. So, I will not discuss that one. So, this much is enough for your reinforced earth retaining wall. Next actually, as I have mentioned that we have spent 2-3 weeks on this topic. So, I will just quickly summarize what we have learned through this. Actually, we have considered one case actually earth pressure at rest, that means when wall there is no movement of wall, and when wall moves from backfill, that means that at rest condition there will be some pressure, and when wall moves from the away from the backfill, pressure will be slowly reduced, that is active. When wall moves away from the backfill, that is called active, and that active pressure will be reducing. So, if there is small suppose if there is a wall, if this is the wall and it moves here, this is active. So, pressure will be reduced, further it is moved this much, still it is active, but there will be some movement beyond which if you move, then wall will collapse. So, that is the limit actually, that means just before the verge of failure, whatever pressure actually developed, that is actually earth pressure, active earth pressure. And similarly, when wall moves, this direction again suppose this much movement, this much movement, this much movement, all are passive, but when it achieved just before the failure, that condition actually is called passive pressure. So, that is what is summarized here. You can see when active case means when wall moves out and when wall moves in, shear stress on failure plane reduces, that is what we saying, lateral pressure reduces. Okay, it is compared to here, it is less here and this is the minimum. If you make smaller than that, then wall will fail. The minimum lateral stress achieves when the soil fails and full strength is mobilized, whereas in passive case wall moves in, that means towards the backfill, shear stress on failure plane increases, lateral pressure also increases, maximum lateral stress achieves when soil fails and the full strength mobilized. So, between active and passive, what are the differences? These are the differences. Next actually we have seen that there are different condition, this is a wall and if I consider an element and at rest condition, what is the state of stress? So, this is the vertical stress and this is the lateral stress and this is the failure envelope. So, when at rest condition your failure envelope will be below the your Mohr circle will be below the envelope, whereas when it is a active case you can see it was initially vertical stress at this is also vertical stress and at rest condition this was the lateral stress, and slowly because of the movement of the wall lateral stress will be reducing and it will reach to a minimum at this point. Okay. So, that is actually called lateral stress or passive active earth pressure, and when you draw the Mohr circle through this, then it will be tangential to the envelope because it is just before the failure. Similarly, when the wall moves this direction, then initially your vertical stress at rest it was here and slowly it will be increasing because of the wall movement in this direction, and when it will be just before failure it will be achieve this maximum value. So, that time if I draw a Mohr circle through this, then that also will be becoming tangential to the envelope. So, this is at rest, this is active and this is passive. And we know that that when wall actually the soil movement, if I consider different one, if everything is giving you active, but at what angle it will actually reach to failure, that gives you actually by geometry you have could find out that critical angle is 45 degree plus pi by 2 for active and corresponding active thrust is half gamma A square K A and active earth pressure coefficient is 1 minus sin phi by 1 plus sin phi. Similarly, you can see when it is a passive, that means when the wall, this is the wall, when it moves here the wall again takes different ways we can consider at what angle actually it will be reaching to the failure, that critical angle geometrically got beta critical actually 45 degree minus phi by 2, corresponding pressure we have got half gamma A square K P and corresponding earth pressure coefficient for passive earth pressure 1 plus sin phi by 1 plus sin phi we have got it. So, this is in detail we have done already. So, I am just summarizing. Similarly, if it is a based on Rankine's theory, if I draw a Mohr circle for active case, this is sigma 1 and this is sigma 3, sigma 3 is the lateral pressure, and if I consider this an envelope will be tangential. Now, if I consider this triangle, from there if I express sin phi and simplify, then I can express sigma 3 in terms of sigma 1 or gamma h, and then it is sigma 3 will be gamma h times this. So, this is nothing but your K A, that is either tan square phi, or I can write gamma h 1 minus sin phi by 1 plus sin phi, that also can be written. So, that means your K A will be equal to tan square 45 degrees minus phi by 2 or 1 minus sin phi by 1 plus sin phi. This way can be expressed. Similarly, if it is a passive case, you can see here passive case actually initial sigma was here and this become sigma 3 lateral pressure sigma 3, though it is principally supposed to be sigma 1, but I am denoting lateral pressure as sigma 3 because of that, and this will be tangential. Now, again if I take this triangle, if I express sin phi, and finally, if I simplify, sigma 3 can be expressed as gamma h tan square plus 45 degrees plus phi by 2, or gamma h equal to gamma h 1 plus sin phi plus 1 minus sin phi. So, that means, this is actually your K A equal to 1 minus sin phi by 1 plus sin phi, and K P equal to 1 plus sin phi by 1 minus sin phi. That means, K A equal to 1 by K P. So, one if you calculate, other one need not calculate, just inverse of that. Similarly, if there is a, as I have the based on Rankine's theory, as I have mentioned that vertical wall and level backfill, but if it is a inclined backfill, then corresponding earth pressure coefficient also can be obtained like this K A K P, and we can consider the direction of the pressure like this, and based on that we can do all calculation which I have shown already during solving the problem. And similarly, now when there is C phi soil, and then your this envelope will not pass through the origin, it will be intersecting the y axis as CR axis, and it will be meeting x axis somewhere here. That means, if I complete this triangle, from there also I can express, considering this triangle, I can express sigma 3 in terms of sigma 1 and cohesion, that is when there is C phi backfill, and that is the when it is active case, sigma 3 can be expressed like that, sigma 1 K A minus 2 C root K A, and when it is a passive case, sigma 3 can be expressed as sigma 1 K P plus 2 C root K P. And pressure diagram I have shown that when it is a active case, pressure diagram will be something like this, and when it is a passive case, your pressure diagram will be something like this. Okay. So, these are the things, based on that how much depth we can do without support, etc. also I have discussed. This is the depth of tension crack, and then double the depth of critical depth will be the depth up to which we can excavate without support. So, these are the things we have discussed in length. I hope there will not be any problem. Next thing is, while solving problem, what I have done. So, suppose there is a pressure diagram, suppose you have better, I will take two parts. There is one pressure diagram, then because of the water, this is the pressure diagram, because of the surcharge, maybe this is the pressure diagram, like that. Okay. So, when this type of pressure diagram, and I have for the stability analysis, I have shown some calculation. Generally, I have divided it into three parts, 1, 2 and 3, 4 and 5. Okay. So, what you have to do? You have to find out P 1, first of all you have to find out P A 1, then P A 2, then P A 3, P A 4 and P A 5. So, P A 1 is what? Nothing but this area of this diagram, P A 2 means this area of this diagram, P A 3 is area of this diagram, P A 4 is this diagram, P A 5 is this. So, P A finally will be equal to P A 1 plus P A 2 plus P A 3 plus P A 4 plus P A 5, like that. Okay. And then finally, we need to find out the point of application of the resultant force. For that, actually what you have to do? You have to find out the lever arm of each. So, if this is the one, for this one, from with respect to this one, if this one is acting, P A 1 is acting here. So, this lever arm will be equal to, if this is H 1. So, this will be H 1 plus, this is suppose H 2, this is suppose H 2. So, H 1 plus H 2 by 3, because this one will be 1/3 from the base, H 1 plus H 2 by 3. Similarly, if this is P A 2, this distance will be nothing but this distance will be H 1 by 2. Now, this is suppose P A 3. So, P A 3 at what height it will work? This will be actually H 1 by 3. So, and this is suppose P A 4. what height it will be? This will be again, this is, if this is h1. So, this will be h1 by 3 and this is suppose P A 5. So, then what is the height this one? This is nothing but suppose h1 plus h2 by 2. So, total height of by 2, because it will be a rectangular diagram. So, finally, resultant we get, how we get resultant? We get our point of application we get, suppose y will be equal to P A 1 h 1 plus, it is not really h 1, the lever arm, suppose y 1, I say y 1, this is suppose y 1 and this is suppose y 2, this is suppose y 3, this is suppose y 4 and this is suppose y 5. So, P A 1 y 1, P A 2 y 2, P A 3 y 3, P A 4 y 4 plus P A 5 y 5 divided by P A. So, if I do this calculation, we get y bar from the base of the. So, and then using that. So, quickly when I have done this calculation, how I have done actually the differarm, this actually what is, where actually it is acting from the base, this is nothing but this distance plus 1/3 of this height. Similarly, P A 2 where it is acting, it will middle of this rectangle. Similarly, P A 3 where it is acting, it is 1/3 of this height. So, like that we can calculate. So, like this everything I have shown, I hope this will be helpful. So, this is the summary of stability analysis and earth pressure calculation and stability analysis of the retaining wall, and I will close this one here. Thank you.